Thank you very much, Abik. I'm very pleased to be here. Good morning. So we'll spend this week together. I hope it will be a pleasant week for you. And I hope that it will be a hard week for you. Just have lots of things to learn. First of all, can you hear me well? Okay, very good. So we are going to talk about phase field modeling. Now, I'm on the basis, I'm a physicist. So you might ask yourself a first question, why am I teaching here in the Department of Materials? So let me explain very briefly how I came to this field. What I'm actually interested in is pattern formation, or more precisely, complicated structures. If you learn science, you are trained in math, usually on examples like spheres, cubes, pyramids, cylinders, or other simple geometrical objects. If you look around you a little bit attentively, you will see there is many things that do not fall in this category. Okay, so here I put up a few examples, but just look around you this afternoon. You will see many examples, to start with the trees that grow outside. So you will see that the world is full of complicated ramified structures. We are also full of complicated ramified structures. The lung, our vascular system, our nervous system is all complicated ramified structures. So what I'm interested in ultimately is, how do these structures form? How do they work? How do they grow? Okay? So this is obviously a very difficult question for complicated things as the lung. So I'm interested in looking at model systems. And one paradigmatic model system for the growth of ramified structures is this. It's very rare in India, at least in South India. To see it in India, you have to go to the north, to the mountains, but it's very abundant in Europe. We have not yet had it, but I hope to see some during my winter holidays. So this is a snow crystal. So this is just water in its solid state. It's ice. And you can see that's a very complicated and beautiful looking ramified object. You also can see that it has some symmetry. And as we will discover towards the end of this course, these symmetries are actually created by the crystal structure of ice. So ice is a hexagonal crystal. And the snowflake, well, as you can see, has 6 arms. So this is related to the 6-fold symmetry in the planes of the hexagons. And in addition, it so happens that ice crystals have a hard time growing along the z-axis of the crystal structure. That's usually why a snowflake is flat. I mean, it's quite flat and has 6 arms in the branches. So the structure of the object is determined by its crystal structure. Okay. Now, of course, this is a very beautiful picture, but what's the use of studying snowflake? Well, I have openly to admit, besides the applications in sort of the analogies with other ramified structures in pattern formation, there is not so much practical interest in studying snowflakes. On the other hand, snowflake is one example for what is called a solidification microstructure, and these have plenty of applications, because if you go to metallurgy and if you look at metallic alloys, that is mixtures of various metals, when you solidify them, you all know that the resulting material is not homogeneous. It presents a microstructure. This microstructure can just be polycrystalline, that is, the solid can be disposed of several grains. It can also consist of several phases, and the geometrical arrangement of these different phases is called a microstructure. Now, the most abundant one that we will hopefully simulate at the end of this course is the dendrite. So this is in some sense the cousin of the snowflake in metals. So you see again, it's a ramified structure, tree-like. That's where the name dendrite comes from. Here the symmetry is different because most metals are cubic. So here the arms are growing like along the axis of a coordinate system. That's again the result of the crystalline structure. So actually, just for the curious how this picture is taken, actually when you solidify metals, you have solidification shrinkage. That is, the solid occupies a smaller volume than the liquid, and you can form pores. And this is a scanning electron microscope picture of the wall of such a pore. So these dendrites have formed within a liquid, and then the liquid has retracted to form the pore, and that's how you can see these things. Normally, if you take a block of steel, you cut it in two, and you look under the microscope, you see the rests of these dendrites that are buried inside the solid matrix. So that's how you normally see dendritic microstructures in a micrograph. So this is very important for materials properties, and that's why we would like to understand this. Now, so I have motivated why we want to understand such structures. Now, what's the difficulty? Well, the main difficulty is quite obvious. These structures are geometrically very complicated. Now, in addition, there is another difficulty. These structures all form during a phase transformation, solidification, and they are not equilibrium structures. Okay? Because if you would say, okay, I have one phase inside another phase, what's the equilibrium state? The equilibrium state would just be a sphere of one phase inside the other phase, because that's the state where there is the least surface, so it's the minimum energy state in some sense. So clearly, this structure is not an equilibrium state. It was shaped by the solidification process, so it is the result of a non-equilibrium process, which means that in order to understand the properties of this structure, we need to follow this non-equilibrium process. That is, we cannot just work on this final structure, we need to understand its history, its growth. So not only do we need to describe this complex structure at one time instant, we need to describe its evolution, how it grows from a simple nucleus into this ramified structure, which means that we have a geometrically complicated structure, and we need to follow its dynamics. Okay? So what do I mean by dynamics? Well, this structure is geometrically complicated because its surface has a complicated geometry. Okay? The surface is the interface between several phases. So in order to understand these structures, we need to follow the interfaces in time. So we need a description of the interfaces, and that's precisely where the phase field comes in, because that's one method to describe the dynamics of interfaces, and that's what we are going to get into during this week. Okay? So on a very fundamental and very basic level, the phase field method is a method to describe the dynamics of interfaces. And as I will explain you in the next few days, its roots lie in the physics of phase transitions. That's why it's particularly suited for describing things like solidification or solid state phase transformations, where the interfaces are between different thermodynamic phases. For this, it's very natural. You can extend it to other interface motion problems. We are not going to talk about this during this week because we would need more time for that, but it's a very general method for studying interface motion. Now, to sort of locate this a little bit better in the toolbox of methods that are available to describe materials, we need to talk about the different representations that you can have of interfaces. Okay, of interfaces between two phases. Of course, you can look at interfaces at various scales. Now, what you are familiar with and what you see in these pictures, in some sense, is the macroscopic scale. So on the macroscopic scale, you see one domain filled by one phase, another domain filled by another phase, and the surface just looks like a smooth surface. Means on the macroscopic scale, the interfaces are just mathematical surfaces without thickness. So if you draw this on a two-dimension on the board, you would just draw a line and say this is the phase boundary. Okay? And the line means a mathematical line, it has no thickness. So then if you want to describe the motion of an interface, you have to write down equations that describe what is the motion of this line, or what is the motion of a surface in 3 dimensions, a 2-dimensional surface in 3 dimensions. And this language is called a free boundary problem. Now, why is this called a free boundary problem? Well, as I said, we need to solve the problem of the evolution of these structures. Now, it's very easy to understand that if a structure wants to grow, normally it needs something. It needs more material, it needs energy, it needs something. These quantities, energy and material, need to be brought to the structure. So this transport process needs to be described, and usually it's described by some partial differential equation, either the diffusion equation or fluid flow equation, or maybe there's elasticity. So there will be some macroscopic transport equation, and we need to solve this with the boundary condition that is taking place at the surface. Because, for example, here the crystal needs to absorb matter in order to grow. Okay? So the mathematical formulation that you can think of in the macroscopic scale is we need to solve a transport equation in the whole outer space with a boundary condition on that surface. Okay? But then, as I have said, the surface moves. So it's not simply a boundary value problem where you solve a PDE with a boundary condition on some surface, because this boundary itself is going to move. And the motion of this boundary is itself a part of the solution of the problem. And that's why this kind of problems are called free boundary problems, because you have to determine the solution of some set of partial differential equations together with the evolution of the boundaries of the domain. Okay, so this is a very general class of problems which are called free boundary problems by the mathematicians. Okay, and so this is the macroscopic view of interface dynamics. You write down transport equation, you write down boundary conditions at the interfaces, and then you write down an equation of motion for this interface. And then you have to solve it. This is a perfectly well-posed problem, but it's very hard to solve. Okay? So that's why we are not going to take this approach. Now, if you take the radically opposite approach, saying, well, okay, instead of looking at matter on the macroscopic scale, to look at it at the microscopic scale, then you know that matter is made of atoms. Okay? And so then you have to describe somehow the atomic structure of your interfaces. Okay? Now, if you think about the solid-liquid interface, we will see some atomistic pictures of such interfaces later. But just picture a solid is an ordered structure. The atoms are arranged on a regular crystalline lattice. The liquid is a disordered structure, so the atoms are a random packing in some sense. So the interface is the transition region where you go from an ordered structure to a disordered structure. Okay? So, of course, this is easy to picture. Now, if you want to describe this mathematically, it's very complicated because you need to have the positions of all the atoms specified, and then you need to decide whether you are in the ordered part or the disordered part. This is possible. People are doing this in what is called molecular dynamics simulations. But this is limited to very small length and time scales. So it is useful, but it is not the right method to describe entire microstructures. Because microstructures, as their name tells, they are on the characteristic scale of microns, and they evolve on the scale of seconds or days. So these are not the appropriate scales for molecular dynamics. So the phase field method is actually somewhere in between. It's often called a mesoscopic method. Mesoscopic because it's on a larger scale than atomistic, but it's on a smaller scale than the macroscopic world. Meso in Greek means in the middle. Okay, so you see I have drawn the box here in the middle between the two extreme boxes. So we'll take, in some sense, the good parts of both worlds. That is, the phase field model is a continuum theory, so we will not specify the position and velocities of individual atoms. We will work with fields, so phase field method. Phase field means it's a field that is as a function of space and time, a continuous function of space and time. This encodes the interfaces, and the basic idea is, why is it called phase field? It's because it's a field that indicates in which phase we are. So it will indicate whether we are solid or liquid in the example that I have shown before. And of course, it has to have interfaces, and these interfaces are continuous. That is, the field varies continuously from one value to the other, but the interfaces are localized and have a fixed thickness. So these are continuous interfaces that have an internal structure. So it's interfaces with a finite width, but they are localized in the sense that they occupy only a small fraction of space. Okay? And that's what we are going to talk about. And there is, in some sense, two opposite and complementary ways how you can motivate, use, and understand phase field models. And these two approaches are indicated by these two opposing arrows. So there is what I would call, in somewhat modern words, there is the bottom-up approach and the top-down approach. So what is the bottom-up approach? This is, in some sense, the classical enterprise of statistical physics. That is, if I have a microscopic picture of the world, that's my fundamental equations. And I should be able to explain from this fundamental microscopic equation the behavior of the macroscopic world. So what we will do today actually is to try to motivate how you can get phase field models from a more microscopic picture. That is, how you can go from here to there, how you can obtain physically reasonable equations for this interface evolution starting from a microscopic model. And so this is, as I said, a sort of traditional approach. It started actually, I would put the birthday of this kind of theories with the theory of van der Waals of the liquid-gas transition. So this was in the 1880s. So people have been working at this for more than 100 years, almost 150 years. He was the first to formulate a continuum theory for interfaces. And as far as the interface structure is concerned, it's essentially the same that we still use today. Okay? And since then, of course, there has been a lot of work. But so this is an effort that has been ongoing for quite some time. Now, what's much newer and what will interest us here is the second arrow. This is much more recent. I would say this dates back only about 30 years. And it's not by chance that this started late, because actually this idea can only be useful if you have computers. Because if you want to do modeling of structures, what you want to have is efficient models. Okay? So I've mentioned it's easy to write down free boundary problems. It's hard to solve them. So you can see phase field methods as a numerical tool for solving free boundary problems. And in that perspective, you can say, okay, what is a phase field model? Well, here I have a free boundary problem, and I have it's difficult to represent the interfaces, which are mathematical surfaces. So you can see phase field models as a sort of regularization of such a problem. That means instead of having a sharp interface, I give the interfaces a finite width, and I make them smooth, because if I do that, then it's much easier to treat them on computers. Okay? This you will see in the practical tutorials. Phase field models are really very easy to handle on a computer. You need standard methods. In a few hours, as you will see, you will be able to program and use simple phase field models. So it's extremely easy. And so the idea that came up about 30 years ago is, well, we should use this kind of model in order to understand free boundary problems. And in that sense, phase field models can be seen as a computational tool. And in that sense, why do I call this a top-down approach? It's you start from this macroscopic view. You say, okay, I want to solve a problem. And then you construct a phase field model which obeys the same equations as this free boundary problem. So in some sense, you engineer a model. And in that perspective, you do not necessarily need a connection to some microscopic physics. Okay? You can postulate that this should just be a numerical tool to solve the free boundary problems. Okay? So these two approaches exist, coexist in some sense, and are both legitimate. And the point that I will try to make in this course, that actually the best possible situation is if you combine the two, or say you can take elements from both of these approaches. The advantage of taking models that are bottom-up, that is, that are motivated by some microscopic physics, the advantage is that they naturally contain the right physics. So if you build them from some physically consistent models, a whole lot of effects that you want to model anyway are already built in. Like, as we will see, the capillary effect, something like the Gibbs-Thompson effect, which modifies the interface thermodynamics as a function of curvature. It is automatically built in the models that are of this type, that come from some microscopic physics. So this is very useful, because precisely you don't need to put them by hand. But then, on the other hand, some properties of these microscopic models are not really very nice if you want to model some specific free boundary problems. So sometimes you have to start from these models and then change a few parameters or a few parts of the equations in order to have a better link between a particular free boundary problem and a phase field model. So this I will comment on more specifically in the last course of the week, when we have sufficient knowledge about this part in order to be able to appreciate how the interplay of these approaches can be an optimal phase field model. Okay? So then here is the course outline. So we have 5 days. So today I will talk to you mainly about this bottom-up approach. That is, we will see a complete example how we can go from a microscopic model to a phase field-like model. Tomorrow we will study this very simple phase field model, and I will review with you some typical ingredients of all phase field models on the example of this simple model that we have developed today. Wednesday we'll talk about phase separation, that is how you can describe spinodal decomposition, precipitation, and things like that. Thursday, we'll talk about solidification, and Friday, I will sort of give you an outlook that will sort of wrap up with what I have just said on the slide before, how you can construct efficient phase field models, what you need to do, and how you can combine the two perspectives for other applications. So, what I want also to say is we are going to go into this course. This is a lecture, but of course you should feel free to ask questions during the lecture, okay? Or to interrupt me if you don't understand something, or if something is completely unclear. Please do not hesitate to raise your hand and to ask a question. Often this is very good, and I will not be upset at all. On the contrary. Of course, I will also be available after the lectures to answer your question. And probably I will attend most of the tutorials, at least part of the time. So if you need some time to think it over and to ask questions later, of course, I will be available for that. I didn't ask, but will the presentation be made available, maybe, or? Okay, well, I think I will leave the slides that I will show. You can make them available to the students. There's no secret about that. So that means that you do not need to write everything that's on the slides. As I have already mentioned, I will also use the blackboard. So for this, you will need to take some notes. Okay, so today we will speak about the bottom-up approach. That is, we will go from the Ising model to an equation that is called the Allen-Kahn equation, or also model A, which is in some sense the simplest phase field equation that you can have. Now, what's the Ising model? The Ising model is a very simple model for a magnetic phase transition. I will introduce and study it in detail with you in the lecture. Now, there is various literature on this subject. One of the best articles, unfortunately, is not very accessible because this is in a book, but it's very good. It's written by Jim Langer, which is one of the inventors of the phase field method in its modern form. Okay, he published the first. He developed the first model that was called phase field model in '78, I think. I don't know. I have a scan of this, but I think it's quite illegal if I make it available for you. But well, now there is one book about phase field models, which is this book by Provatas and Elder. I have. Well, it's not my favorite book. It's but it's good, and it is the merit to be there. And what's more, now I reveal a secret to you. If you type the title on Google, you will come on Nick Provatas' website, and he has the PDF of it available. So you can download it. I don't know how he deals with his publisher, because I think probably it's illegal. I mean, the publisher wants to sell the book, so I don't know how he can put it up onto his website. But I tell you the secret because, well, this way you can take advantage and download the book. Actually, in this book, more or less everything that I'm going to tell you this week is there, not necessarily in the same order, but you can find all the information and, of course, much more because it's 300 pages. Okay? Then I have myself published some review papers. Probably one that's relatively readily available is this one in Handbook of Crystal Growth. And one thing that I haven't put up, I have a few months ago published also a paper in this review of the Indian Institute of Science. Okay, so this will concern rather the lecture on Thursday. I will use this as a basis. So there is various literature available on this subject. Okay, so maybe now it would be not bad to switch off the projector, because now I will switch to the blackboard. Because what I will do next is I will, okay, in some sense, phase field models, as I have said, come from the physics of phase transition. The physics of phase transition comes from statistical physics. So we will need some tools to really understand the origin and the foundations of phase field models. We will need a few basic results of statistical physics. Now, Abik told me that you have not necessarily all heard an extended lecture on statistical physics. So what I will do in the next half an hour, 45 minutes, is I will do a little crash course for you on thermodynamics and statistical physics. Of course, since it's 30 to 45 minutes, it cannot be a full course on statistical physics, but I will try to justify for you the most important relationships and formulas that we will need in order to develop the phase field model. Okay? Now, the motivation for doing this, in some sense, is exactly the one that underlies this slide with the 3 green boxes, with the 3 different scales, macroscopic, mesoscopic, and microscopic. So it's about the link between the microscopic and the macroscopic scale. That is the link between the microscopic physics and thermodynamics. Thermodynamics is the description of matter on the macroscopic scale. The question is how we can justify this thermodynamics from our knowledge of the atomistic nature of matter, right? So that's the basic subject of statistical physics. So I will also take this opportunity to review a few facts of thermodynamics that will be useful for the course, and I will try to restate some concepts that you certainly know, but that might be useful to remind. So I'll start a few minutes on thermodynamics. Okay. And I told you this is macroscopic, so thermodynamics was developed in the 19th century. And why it was developed in the 19th century? Because the basic tool in the Industrial Revolution was the steam engine. And thermodynamics you can see as the science of steam engines. Okay? So what we'll have in mind when I develop you the following formulas is a steam engine that is its gases that are enclosed in some vessels and that are heated. Okay, so that's the basic concepts that you have in thermodynamics. And one of the, of course, foundations that you learn is the first principle of thermodynamics. That is, you have something that is called the internal energy. And this is, in some sense, the total energy stored in a piece of matter. And you learn that if you want to change the internal energy, you can do it in two ways. You can either do mechanical work, or you can have heat exchange. Okay? And then you learn that the mechanical work, well, for doing mechanical work, you need to change the volume. The minus sign is here because you increase the internal energy when you do work on the system, so when you compress it. And then the heat exchange, actually you learn that you can describe this by a function that is called the entropy. So the quantity of heat that is exchanged is equal to TdS. Now I just, as a little preview, want to say that there's actually one thing that is missing here that is never taught in the basic thermodynamics courses, and that's again because it's the science of steam engine. Because in a steam engine you work with a gas enclosed in a vessel, but there is a third way how you can change the internal energy of a gas, that is by adding or removing matter. Okay? And so there should be a third term here, which I will write directly as mu dN. Okay? So dN means that you change the number of moles or the number of molecules that are in the vessel. You pump in or you extract some gas, and the energy that you have to pay per particle is called mu, which is called the chemical potential. Okay? Good. Keep this in mind. I will not necessarily write it all the time, but it will show up. It will show up later. So, if you have this expression for the internal energy, you see this is a differential. So what's behind the d's are the variables of this function. So u is a function of the variables s and v. Okay? And you learn in thermodynamics that u, the internal energy, is a state function. Okay? So for given conditions of the gas, it doesn't depend on the path that you take to go from point 1 to point 2. And you also learn that you have other state functions that you can form. So I always learned this in this way, H and G. Okay? So the thermodynamic square. So this is the Helmholtz free energy, the free enthalpy or Gibbs free energy, and this is the enthalpy. So what does the lines mean? The lines mean some transformations. Here in this direction you do minus Ts, and here in this direction you do plus PV. So these are Legendre transforms, and they change the variables of these functions. So I will just do one example, the transformation from u to f. So I form f is equal to u minus Ts. So if I calculate the differential of f, this is du minus TdS minus SDT. If I use my first principle for du, so this is minus PdV plus TdS, and now I just copy minus TdS minus SDT. You see that these two cancel, and that in the end I get minus PdV minus SDT. Which means that now my variables here are V and T. So I will just write the variables. So this depends on T and V, and this depends on T and P, and this depends on S and P. Okay, so these functions are called thermodynamic potentials, and which one you have to use depends what are the conditions under which you want to work. If you want to work under constant pressure, you should use one of those. If you work in a closed vessel, it's better to use one of those, and so on. If you want to work at constant heat content, then you should use those. If you want to work at constant temperature, then you should use those. Another remark that will be useful in the following is if you look at these transformations here, you see that they always associate two variables, Ts. These are called conjugate variables. Okay? And I remind you something that you probably all know. Of these variable pairs, of these conjugate variables, there is always one that is extensive and the other one that is intensive. Okay, so an extensive variable is a quantity that is countable. Okay, so that means that you can measure and count in some sense, such as the number of particles, the total energy, or volume. You can decide, I want to add 5% of volume, and you just add a cube to the vessel in some sense. Or you say, okay, I want to add a quantity of energy, and you can change it. The other quantities, the intensive quantities, are not so easy to count. How to count temperature is not obvious. Right? So they are of different nature, and it's not by accident or by chance that the two are associated. It's in some sense, as we will see, you can put constraints on the extensive variables because you can block exchange of extensive quantities, or you can allow exchange of extensive quantities. A very simple example that is obvious is if you have a volume and you have fixed walls, and for example you change the temperature, then you change the pressure inside the vessel. Okay? Instead of that, what you can do is you can put a piston on one side with a spring. That means you fix the force the pressure with which you push on the wall. Now if you heat, the system can expand or compress, so the pressure will stay the same, but the volume will change. And what you have changed between the two situations is the boundary conditions. Okay? So you can put boundary condition on extensive quantities. It's harder to put boundary conditions on intensive quantities normally. Okay? And we will see why is this in the statistical mechanics view of this. Okay. Yes. So what I will tell you in the next half an hour is how you can link this language of thermodynamics to the description of matter by microscopic physics. So I want to do a little parenthesis because there is something really easy to explain, but which normally is probably not very present in your mind, which explain you why statistical physics works so well. Okay? Actually, I can quote a famous man who is Albert Einstein, who said something like, he believes that any theory can be wrong except statistical thermodynamics. Because, as you will see, it uses extremely few hypotheses, and you can derive a whole host of things from it. It's really nice. And what's the basic? Actually, the very basic at the heart of it is just the theorem of big numbers, or the central limit theorem in some sense. And I will make you a very simple example. So this is in some sense part 2. Why does it work? Okay. Now consider a very simple situation. Consider a vessel where you have a wall. So this is the left part and this is the right part. And now consider that you put a little bit of molecules in the left part. And then you take out the wall and you want to analyze what happens. And the question, a bit provocative, is with which I will start is, what's the probability to find all molecules in the left part, even when there is no wall? Okay? Now, just think about elementary probability theory. It's not hard to answer this question. If you have one molecule, and if the vessel is exactly symmetric, the probability to be on the left is equal to 1/2. Right? If I have n molecules, of course, you suppose that the molecules are independent, and then you see that the probability to have all to the left is just 1/2 to the n. Elementary. Now, what makes this sort of useful is that for the real physical world, n is enormously large. You know that the Avogadro number is 10 to the 23, and that 1 mole occupies 20 liters in normal conditions. So we have in this room something like 1,000 or 10,000 moles. So we have 10 to the 26 molecules. So it's physically perfectly allowed that all air molecules go up there on the balcony. Only the probability for this to happen is 1/2 to the 10 to the 26, which is about 10 to the 10 to the 25. That is, it's about 1 by 1 with 10 to the 25 zeros behind. Okay? And that's fortunate for us, because if there was only 10 molecules in the room, then it would happen every 100 seconds that all the molecules are over there. Okay? Now, of course, you can be a little bit more precise and say, okay, now I'm interested not in the probability of finding all molecules to the left. What's the probability to find NL molecules to the left? Well, this is again elementary probability theory, because left-right is a binary variable. So this obeys a binomial distribution. So you will have that this is 1/2 to the n. And then here you will have the binomial factor, which tells you how many possibilities there are to put particles to the left or to the right. So here I will have n factorial divided by nl factorial and nr factorial. Okay, so this is an exact expression. And if n is large, then you can develop this thing, and you can use the central limit theorem. So this is approximately equal to a Gaussian. So you will find that this is exponential to minus nl minus n by 2 squared. N by 2 is the most likely state. Okay, that's where this factor is maximum. And then you have a 2n here. Okay. So, yes? Ah, yes, I should not use the lower part of the board. Okay. Well, I will just write, okay. I will write this a little bit higher up, and then 1/2 to the n factorial to nl factorial, nr factorial, and then I will write this again. That is exponential to minus nl minus n by 2 squared. Okay. So I'm not doing this explicitly. This is nothing but the application of the central limit theorem. You can find this in many books, but this is just math. You develop the factorials, and you find this. Also, this formula is really elementary probability theory, so there is no mystery in there. Now, there is one important consequence of this. You see, this is a probability distribution. So you see that the most likely value for the number of molecules to be on the left side is n by 2. Then you have fluctuations around this, and the fluctuations are given by the variance of this probability distribution, and the variance is what is on the bottom, or more precisely, if you want the standard deviation of NL, it is square root of n, because this is the variance. The standard deviation is the square root of the variance. So NL is equal to n by 2 up to an incertitude of square root of n. Okay, and now what's interesting is if I want to know the fluctuations of the fraction of molecules that is to the left. So I form the relative variable NL by n. Okay, so you see that this is equal to 1/2 plus or minus, and now I need to divide square root of n by n, so 1 by square root of n. Which means that statistically I will find half of the molecules to the left with a fluctuation of the order, with a relative fluctuation which is of the order of 1 by square root of n. And if n is 10 to the 24, then the relative fluctuation will be 10 to the minus 12. And this is the order of magnitude of the fluctuations of all quantities. So suppose you put a pressure sensor here. It would measure 1 bar. In reality, this pressure fluctuates, but the fluctuations are of the order 10 to the minus 12 bar. That is much smaller than the sensibility of even the best pressure sensors, so you will not see them. Okay? So basically what thermodynamics is, it's the equations for the averages that you can get from statistical physics. And since the number of involved particles is so large, fluctuations are so small that you do not see them in macroscopic systems, and that's why thermodynamics works so well. That's the reason for Einstein's remark, because the central limit theorem is really very powerful. Okay. So let's come to the connection of statistics and thermodynamics. Okay. This dates back to Boltzmann, who made a very daring, who was the first to make this connection, because he, in his time, end of the 19th century, the atomistic hypothesis became admitted. So he was thinking about how you could make this connection. And basically his postulate, which is the only postulate that you need to build statistical mechanics, is the following, is that I can define the entropy by this formula. Entropy is equal to Kb log of W, where W is the number of microscopic states. Now, where does this come from? Actually, he was considering an isolated system. That is a system where you fix the volume, you fix the energy, and you fix the number of particles. Okay? In practice, it's very hard to do, especially for the energy. You need a very good thermos bottle to do that. But, well, in your mind, imagine a system that can not exchange anything with the surroundings. That's an isolated system. And the fundamental hypothesis is, well, if I put some particles in there, and if I do not know anything more than the energy, the number of particles, and the volume, then of course there is many microscopic states that are compatible with these constraints. Okay? For example, the energy can be kinetic energy. I can distribute this kinetic energy in many different ways on the different atoms. So there is many microscopic configurations that are compatible with these constraints. And if I do not know anything more about my system, the most reasonable hypothesis that I can make is that any of these microscopic states have the same probability to occur. And you have often heard that entropy can be seen as a sort of measure for disorder. So that hypothesis is that, well, if I have more available states, then I know less about my system, and then the entropy is higher. Okay? So that the entropy is an increasing function of the number of available states. That seems a quite reasonable hypothesis. Now, why the logarithm? You can motivate the logarithm quite easily, because if you have two systems, 1 plus 2, you would like the entropy to be extensive. That is, if I have the total entropy should be entropy 1 plus entropy 2. Okay? Because we have seen entropy is related to the heat content. So if I have two identical systems, I put them together, I should double the entropy. Now, if I think about the number of microscopic states, if my system 1 has a number W1 of microscopic states, and my system 2 has a number W2, well, if I look at the total number of microscopic states available, actually I can choose my state of system 1, and then independently I can choose the state of system 2. So the total number is the product of the individual state numbers. And that's why I need a logarithm, because only with a logarithm I will get the addition of the entropies. Now, of course, there is a question, how do I calculate the number of microscopic states? Now, I'll not go into detail about this, because this would take too much time. Actually, the ultimate and rigorous explanation how to calculate W comes from quantum mechanics, because quantum mechanics tells you that there is a discrete state space, and you can count the number of available eigenstates of the Hamiltonian. So it will rigorously give you the natural answer for W, no matter what's the system. Okay, Boltzmann came before quantum mechanics. He couldn't use this. So he actually not postulated, he correctly said that actually the number of microstates would be proportional to the number of ways an atom can choose its state. So what's the state of an atom? State of an atom is given by the position and by the velocity. So the position, of course, is linked to the volume. If you give it a bigger volume, there's more positions to be explored. So the number of states is proportional to the volume. And it's also an increasing function of the energy, because if you give it more energy, the kinetic energy is higher, so you can explore higher velocities. Okay? So just take it for granted that this number of states is an increasing function of the volume and of the energy, which means if I increase the energy, there is more states available. Okay? And just suppose that I can calculate this number of states from quantum mechanics. Just believe me, if I want to go into detail, I need half an hour more. If some of you desire to see this, I can give an extra half an hour after the end. Okay? We just have defined an entropy function. And as I said, this entropy is a function of the constraints that I put on the system. So I told you what I have fixed is the energy, the volume, and the number of particles. So of course, formally I can write down, if I vary that entropy, how should that happen? So I can write down the differential of the entropy. And now I can use the chain rule. I can write ds by dE times dE plus ds by dV times dV plus ds by dN dN. This is just formal. And now I can say I define. I give names to these partial derivatives. So I call this one 1 by t. I can call this one p by t. And I call this one minus mu by t. I can always do that. I can give it names. And what's the motivation to do that? Of course, if you look at this now, if you write all this, and then if I multiply the whole thing by t, then I get TdS is equal to dE plus PdV minus mu dN. And what do we recognize? Well, if I switch sides here, I get dE is equal to minus, minus PdV plus TdS plus mu dN. We have seen this just before. This is the first principle. Okay? So I give these names to these quantities in order to recover the first principle in some sense. Okay. As I said, this is a formal game. I can always do that. What do I get from this? I get statistical definitions of the thermodynamic quantities. For example, I get that the temperature, I get a definition for the temperature, which is 1 by T is equal to ds by dE. Now, if you think about this, this is very remarkable. Okay, because what is the object on the right-hand side? Remember, the entropy counts the number of microscopic states. I have said the number of microscopic states is a function of energy. So the number of microscopic states varies with the energy. And I take the derivative of this number of microstates with respect to the energy, and this is supposed to be the temperature. If you know thermodynamics and if you see this for the first time, you say, frankly, I mean, it seems to be very odd that you can define such an intuitive quantity as the temperature by a simple counting of microscopic states, right? So it's, on first sight, it's very strange, okay? So I just want to spend a few minutes to demonstrate you that this quantity really has some properties of the temperature and how we can get what you all know, that is the Boltzmann distribution, which is again quite elementary probability theory. Now suppose again I have a system with two compartments, and again I put two gases there, So this is a wall which doesn't let pass any molecules. So the number of molecules and the volume of the two subsystems are fixed. But I make this wall heat conductive, so the two parts can exchange energy. Okay? But I suppose that the whole system is again isolated, so that I have E1 plus E2 is equal to E, and this is constant. Okay? Now, as I have said before, the total entropy is additive, so I have that the entropy is S1 of E1 plus S2 of E2. Okay. Now I use some elementary probability theory. I say, what's the probability to have the energy of system number 1 at a particular value E star? So this is equal to the number of microstates of system 1 that I have with E star. Okay. I'll write it a little bit below. Okay. The probability of having E1 equal to some particular value is equal to the number of microstates of that particular energy times the number of microstates of the other system with E minus E star. Divided by the total number of microstates of the combined system. Again, elementary probability theory. I can count all the possibilities that I have to have E star here and E minus E star here, and I divide by the total number of states available for the system. It's a simple counting. Okay. So you see that this probability, I mean, this is just a constant factor. It's the total number of states. So it's just proportional to the product of these two state numbers. Okay. So I'm looking at what's the most probable state. So I look at the max of P. But since the logarithm is a monotonous function, instead of looking for the max of P, I can also look at the maximum of log P. And if I take log P, that is, I have to look for the maximum over E star of S1 of E star plus S2 of E minus E star. I need to find the maximum of this function. Okay. Well, what does it mean? If I look for the maximum, I have to have that the derivative with respect to E star of S1 plus S2 is equal to 0. If I derive this, then this means ds1 by dA star. Then in the other one, E star comes with a minus sign, minus ds2 by dE star is equal to 0. This is the temperature of system 1. This is the temperature of system 2, equal to 0. So I have found that the most probable state is the one where T1 is equal to T2. Okay? So purely probabilistic grounds tell me if I put two systems in contact, the equilibrium state is the one where the temperatures of the two systems are equal. So this very strange statistical temperature really has one of the basic properties of the real temperature, namely that it has to be equal in systems in contact. Okay. Actually, I suggest, now the first hour is over, but I suggest that we continue for 10 minutes, because then the statistical part is finished, and then we'll have 15 minutes break. Okay? Right? Because otherwise I would need to, no, I think it's better this way. Okay? So, now a variant of the calculation that I just did will give us what we know from your elementary courses in thermodynamics, or even from school physics. That is the Boltzmann law. So we are again considering two systems in contact. Only know I will make system 1 small and system 2 big. So it's the same as before. E1 plus E2 is fixed to a total energy, but I will have that E1 is much smaller than E2, which will therefore approximately be equal to E. So I will just write down two probabilities, which will be again follow from elementary probability theory. So the one is the same that I had before, namely that system 1 is at a particular energy E star. So that's the same expression that we already had. It's the number of microstate of that energy of system 1 times the number of microstates, okay, divided by the total number of microstates. And now the second probability is that the system 1 is in 1 microstate I of energy EI, in some sense it's just an application of that. Here I count the number of microstates available with this energy. Here I consider just the probability of one of those. So this number here is just 1 now. So the probability to find the system in one particular microstate with the energy EI is just W2 of E minus EI divided by the total number of microstates. Again, elementary probability theory. Now all we need to do is we need to study this expression here. So W2 of E minus EI by using the expression of the entropy, I can say that this is exponential of S2 of E minus EI divided by the Boltzmann constant. Then I can say that since EI is much smaller than E, I can do a Taylor expansion here. So this is S2 of E, and then I get minus ds2 by dE taken at EI equal to 0 times EI. And if I do that, I get that W2 is equal to a constant, which comes from the constant term here, taken in the exponential. And then I have an exponential. Here I have a minus the ds2 by dE is equal to 1 by the temperature. I have the Boltzmann constant here. And up here, I have the EI. Which means that my probability of being in a microstate, in a particular microstate I, remember Pi was W2 of EI divided by W total. So if I put this in, it's C by W total times e to the minus EI by KT. So, of course, this is again a constant. So we see that the probability to be in a particular microstate I is proportional to e to the minus its energy times KT, which is, of course, the Boltzmann law. This you all know. What you probably know less precisely is the role of this constant up front, which plays a very important role, because you all know if this is going to be a probability distribution, we have to have that the sum over all microstates over the probabilities has to be 1. That means I can calculate this normalization constant. So this is actually called the partition function. So you write this as 1 by z e to the minus EI by KT, and z is just the sum over all the microstates over all the Boltzmann factors, e to the minus EI by KT. So this is called the partition function. And again, if you know what are the microscopic scale available, in principle you can calculate it. As you will see in a little while, it's not always obvious. It's generally hard to calculate this. But if you can calculate this, so it's a purely mathematical construct as soon as you know the structure of your microscopic state space, you can do a lot of things. And I will finish up with this. I will just give you two little formulas that we will use in the second part of the course. So I will leave the definition of the partition function here. Because if you want to calculate the average energy, so this is important. You remember the drawing that I had? This is system 1 and system 2. If I look at system 1 alone, its energy is not fixed anymore. System 1 can now exchange energy with the system 2. So I have opened the barrier for the extensive quantity, which is energy. In exchange, I get that this system 2 actually fixes the temperature for system 1. So I have abandoned the constraint on energy. In exchange, I have gotten that the temperature is fixed. So you see the mirroring of the thermodynamic identities in this statistical approach. Either I fix the energy, then the temperature is given, or I let the energy open, and then the temperature is fixed. Okay, so you can fix only one of the quantities, energy or temperature. Impossible to fix both. So the energy of system 1 now can vary. So there is an interesting question, what's on average its energy? So to calculate the average energy, you can just use the elementary definition of statistical means. So the average of the energy will be the sum over all the microstates I. You take the energy EI, and then you multiply by the probability to find the microstate I. So this is just the definition of a statistical average. Now if you write this down, you have EI, and here if I write the explicit expression for the partition function is exponential minus EI by KT. Oh, let me do one thing that will facilitate things. I will call beta 1 by KT. And then this is called minus beta EI. This is a very standard notation. It's used everywhere. Now, why do I do that? Because it makes the things easier. If you stare at this long enough, okay, you see that actually I can obtain exactly this formula by taking the log of z and deriving this with respect to beta. Now, how does this work? Remember, z is equal to the sum over all the microstates of e to the minus beta ei. If I take the log of this and if I derive with respect to beta, I will first get the outer derivative. This will give me 1 by z. Okay. Then I have to take the inner derivative. The inner derivative is the derivative of the sum. So in each term, if I derive by beta, I will take an e outside times the same exponential, which is giving me this. And I'm also getting out a minus sign, which I compensate with this minus sign here. Okay? So this is a mathematical trick in some sense, but it tells you if I know the partition function, I can get the average energy by a simple derivative. There's many similar formulas which involve log z. So if you can calculate the partition function z, you can calculate a whole lot of things. Okay, now this average energy, in fact, we can identify this with the internal energy of thermodynamics. Okay, and I want just to make one important statement which concerns the Boltzmann distribution. So you see that there is an exponential of the energy with a negative sign, which means that if the energy is higher, the probability for a state to be occupied is lower. So this is very natural because you know that the system has always tendency to go down in energy. Okay? But if you have a finite temperature, actually you can also populate states of higher energy. And then what you will see is really non-trivial because on the one hand, of course, lower energy states have a higher probability. But on the other hand, I have said before that the number of available states increases very rapidly with the energy. So the higher energy states have a smaller probability of being occupied, but there's more of them. And in that sense, the average energy that we have calculated here is really a non-trivial quantity. If the temperature is very low, the average energy will be just the energy of the ground state. But if the temperature is high, you will populate more and more states. So there will be a balance between the energy and the number of available states. So there will be a balance, and this is an idea that will come back. There's a balance between energy and entropy, because entropy is the number of available states. Okay? So that's the fundamental physics of phase transitions, the competition between the energy, which wants to bring you down in energy, and entropy, which will make you populate more states. And we will need one last identity, which I will not prove, which I could prove, with simple elementary probability arguments. Well, there's also some more mathematics involved, but there is a formula that directly relates the free energy F to this partition function. You can prove that log Z is actually directly proportional to the partition function. There's just a factor KT. And you can also prove that the most probable energy corresponds to the minimum of F, okay, which gives you a statistical interpretation of the fact that you know that the thermodynamic equilibrium states corresponds to a minimum of the free energy. Again, this you can prove with some statistical identities, takes 20 minutes, but there is nothing mysterious. So from elementary probability theory, you can prove that the state that you are most likely to see, just like the state half molecules to the left and half molecules to the right that we had in my very simple example, but the state that you are likely to see corresponds to the minimum of F. Okay? So this was the recall of statistical physics. No more statistical physics. Well, a little bit in the reminder, but this was the hardest part. I think you deserve 15 minutes break. Or shall we continue? No, we continue. A little bit break. Okay.